Good morning, students. Today we are going to see the next module, that is resonant circuits. So we have the definition as resonant circuits. Okay, so its definition, we give the definition as a circuit is said to be under resonance when net current is in phase with applied voltage. Okay, or we give it as one more definition as when inductive reactance and capacitance are equal causes electric energy to oscillate between magnetic field of inductor and electrostatic field of capacitance. Okay, these two are the definitions. So resonance occurs only when circuit consists of AC input. AC means it is alternative current, and inductor and capacitor. Okay, then one more key point: resonance is achieved by varying frequency, keeping inductor and capacitor constant, or varying inductor and capacitor, keeping frequency constant. Okay, so these are the two definitions, then these are the two key points. So based on this you can make any circuit as a resonance circuit. So we go for applications. If the application part, if you go for the application, this resonance is applicable in designing the radio receivers and This is used in DSP for filters design, etc. So many things are there. So more detail you will study in the higher semesters about this resonance circuits. So we will go for the our important circuit with constants, resistors, inductors and capacitors. So one more key point, that is at resonance we have the inductive reactance. Inductive reactance is as XL should be equal to XC. This is the at resonance condition. Then circuits becomes, when this happens, the circuit completely becomes purely resistive, circuit. Okay, so first one we will see about the series resonance. So series resonance is, in series resonance we have the resistor, inductor and capacitor in serial combination, that is series combination. So here is the resistance, here is the capacitance, or we can make for better convenience I will make it as inductor only, so in order to avoid confusion. So this, let it be the inductor, then this is the capacitor. Okay, these three are in series combination. This is R, this is L, this is C. Okay, for this combination we apply the AC input. Here we apply the AC input, that is voltage, we can take it as V. Then current flowing through the circuit, let it be I. Okay, then voltage drop across resistor, let this be VR. Okay, from here to here it is VR, then from here to here it is, let it be VL. Okay, VL is the drop across inductor. Then here this, let it be VC, that is voltage drop across capacitance. Then all the voltages and currents, all voltages and currents, all are the having RMS values. This you should note, all are in the RMS values. Then, so what is the total V? Total V is nothing but VR, V subscript R plus VL plus VC. So this, let's take it as equation number 1. Okay, then if I want to represent this in terms of current, so V becomes what? Drop is nothing but I into R plus, then VL is nothing but I into XL plus I into XC. This is capacitive reactance, this is inductive reactance. Then I have common I value, I will take it as outside. So this I will write it as V is nothing but, I can take it as I outside. If I take I outside, so if you want to represent it in terms of omega term, this you have studied in the analog circuits and all, you might have studied. So R plus this I will write it in terms of j omega L plus or minus. So it is not plus, it is minus, because it is the capacitance. So this becomes as minus. So the value is minus j divided by omega c. So you can write it like this. So if I take the I value, this becomes what? I is nothing but what? V divided by this R plus J I will take outside. So this becomes what? Omega L minus omega C. Okay? Omega L minus omega C. So it is capital L, not subscript, it is capital C, omega C. Okay? Omega L, here it is omega C. Okay? Next, if I take the mod value of this, the mod value of I, if I take, this becomes what? Nothing but square root of, it is never square root of R square plus omega L minus 1 by omega C whole square. Okay? So this is the mod value. This only I will represent as this nothing but 1 divided by Z. Okay? So this is the series. Then what is the resonant frequency here? If you want to calculate the resonant frequency, so resonant frequency becomes resonant frequency. So this I will represent as F naught. Okay? So when this condition occurs, when your XL is equal to XC, okay, at this condition we are going to get the resonant frequency. So under resonance, so this becomes what? J omega naught L is equal to minus J divided by omega naught C. Okay? Then J you can cancel out from both the sides. J get cancels. So here it is omega naught L minus 1 divided by omega naught C is equal to 0. So take the LCM. If you take the LCM, it is omega naught square L C minus 1 is equal to 0. So this is omega naught square L C is equal to 1. Then omega naught square is equal to 1 divided by LC. So if you want directly omega naught, you can take it, calculate as omega naught equal to 1 divided by square root of LC. This also you can take. Or if you want to convert this in terms of frequency, so omega naught is nothing but 2 pi F naught whole square is equal to 1 divided by LC. So it is from here. From here I have taken it as this equation. So then we want F naught. So F naught square is nothing but 1 divided by, this is 2 square is 4. Okay? Then here it is pi square, it is LC. So if you want F naught, this becomes what? 1 divided by, if you take square root here, square root of 4 is 2, square root of pi square is pi, then square root of LC. This becomes square root of LC. Okay, this is the resonant frequency for series circuits. So this is in terms of Hertz value. Okay, so if you want some phasor diagrams, so if you go for phasor diagram, so the phasor diagram is like this. So these are the phasor diagrams. So this is I, then here is VL, here it is VC. So when F is less than F naught, when F is less than F naught, omega L is less than 1 divided by omega C. So the VL is, means voltage across inductor is less than voltage across capacitance. So this becomes what? Capacitive circuit. Okay. So in capacitive circuit, so VC is higher, PL is lesser. So the voltage drop is like this. So here the voltage drop across. So this point is VC minus VL. Then here it is VR. Okay. Then when at resonance condition, here this is the I, then here is V equal to VR. This is VL, here it is VC. So here F is equal to F naught. So omega L equal to 1 divided by omega C. So VL is equal to VC. So this is at resistive circuit. This is resistive circuit. Then when F is greater than F naught, so when the frequency is greater than F naught, so this is I, here is VR you will get. So F is greater than F naught, so omega L is greater than omega C, so VL is greater than VC. So this circuit is called as inductive circuit. So here the phasor diagram, VL, here it is VC. So VL is greater than VC means at this point somewhere here you will get. So the voltage drop goes like this. Here is the V. So this point and this point. So here is VL minus VC. So this is about the phasor diagram. So some reactive curves and some Q factor is there, that we will see in the next classes. Okay. Thank you.